tutoring. In this video, we're going to be looking at visible light and black body radiation, and this is video number 4 of 4 for our waves topic. So let's crack on. A lens is a piece of equipment which causes light to bend through refraction. You can study the behaviour of light when travelling through a lens with the help of ray diagrams. There are two different types of lens. You have convex lenses and concave lenses, and both bend the light differently. Convex lenses refract light and bring the rays together. Another way to look at this is to think about light rays refracting to a focal point. Let's have a look at the convex lens in more detail on a ray diagram. So this is what a convex lens looks like from the side. You can see that it's fatter in the middle than what it is on the outside. So here on the left we have a purple arrow and this represents the object. On the right we'll have another purple arrow and this represents where the image will be. The black lines represent rays of light and the red line through the middle is called the principal axis. You draw convex lenses as lines with arrows pointing up and down away from the lens, like this. Now let's have a look at concave lenses. Concave lenses are like this shape here, where they are fatter on the outside than what they are in the middle. So again, we're going to draw in some arrows, and this arrow here represents an object, and this arrow here represents the image. And you can see here that it's a virtual image because the top of this image is a dotted line, and we'll see later on that dotted lines are virtual rays. You draw concave lenses as lines with arrows pointing up and down towards the lens, like this. So you have to know how to describe the picture which comes out of a lens. Lenses are very difficult, but like lots of other things, with practice you'll improve. In the next few slides we are going to have a go at describing the image which can be seen from a lens. So let's describe this image. Well, we know that this image here is real because both of the lines which cross are real lines, they're not dotted lines. We know that this image is inverted, and we know it's inverted because it appears on the other side of the principal axis to what the object is. And we know that this image is larger because this arrow is bigger than this arrow here. This image is real, and we know it's real because both of these lines are not dotted, they're both real lines, they're both real rays. We know that this is inverted because again it's on the other side of the axis to what our object is. And we also know that this image is smaller than what the object is because the arrow is smaller than the object. This image is virtual because the rays which cross are both dotted and they are both virtual rays. That means the image produced is virtual. We know that it is upright because it's the same side of the principal axis as what the object is. And we know that it's larger because, as you can see from this diagram, this object here is much larger than this object here. Or should I say this image is much larger than the object itself. Okay, so now let's have a look at some concave lenses. Well, we know that this one's virtual because one of the rays is dotted. It's a virtual ray. We know that this image is upright because it's the same side of the principal axis as what the object is. And we know that the image is smaller because the image arrow here is much smaller than the actual object. Again, this one's virtual because one of the rays is dotted. We know it's upright because it's on the same side of the principal axis as our object, and we know that it's smaller because the image is much smaller than the object size. So you also need to know how to draw ray diagrams as well as interpret them. So let's have a look at how to do that. The first step is to draw in the ray which passes through the middle of the lens. This one does not refract. So our first step is to draw this line through the middle, and this line doesn't bend when it goes through. It just passes straight through and continues in the direction that it was going in the first place. The next step is to draw in a line which is parallel to the principal axis from the top of the object, and that's done here. Next, we're going to pass this second line through the focal point. And finally, we're going to draw in our image. The tip of the image is where the two rays cross. But what if the rays don't cross? Well, if the rays don't cross, what we do is we trace back the real rays back onto the other side of the diagram as virtual rays, like this. And where the virtual rays cross, we'll draw in our image, like that. And now for concave lenses. So again, the first step is the same. We're going to draw in our first ray which passes through the middle of the lens. And again, this one doesn't bend. Next, we're going to draw in a line parallel to the principal axis from the top of the object, just like we did for the convex lens. Now, step number 3 is different. This time, we're going to draw in a virtual ray from the lens to the focal point on the same side as the object. Then we're going to continue this line on the image side, but as a real ray. And finally, we're going to draw in our image, and the tip of the image is where the two rays cross. Next, we're going to have a little look at magnification. Magnification is useful as it can make images look bigger or smaller than what they actually are. Magnifying glasses use magnification and display images which are bigger than real images. And here is the magnification formula. Magnification is equal to image height over object height. If you're following along in your revision workbook, pause the video now and complete task number 10. Okay, next we're going to have a little look at visible light. Visible light is the part of the electromagnetic spectrum which we can see. The part which we can see is split up into its own parts as well, the spectrum of colours. Can you remember your colours of the rainbow? If you can't, there's a simple way of remembering it, and that's Roy G. Biv, where each of the letters stands for a different colour. You can see that the electromagnetic spectrum has the visible spectrum within it. And just going back to this Roy G. Biv, R stands for red, O stands for orange, Y stands for yellow, green, blue, indigo and violet. As the visible light spectrum is part of the EM spectrum, each part and how far along you are determines the wavelengths and frequencies of that particular light. For example, red light has a wavelength of around 675 nanometers and blue light has a wavelength of around 480 nanometers. Can you remember reflection, absorption and transmission from earlier on? Reflection is where waves bounce off a surface. Their energy is not transferred and the waves do not go through the object. Absorption is where waves disappear after coming into contact with a different medium. Their energy is changed into different types of energy. And transmission is where waves travel through a medium. White light is the light which contains all parts of the visible spectrum. It contains red, orange, yellow, green, blue, indigo and violet wavelengths. Now, if you shine white light into a glass prism like this, you'll see that the white light actually splits up into all of its constituent parts and you'll get basically a rainbow coming out of this glass prism, and that's something quite interesting actually if you want to experiment with that. Colour filters work by transmitting certain colours but absorbing others. Remember, transmission is where it's allowed to go through and absorption is where the light's taken in and transformed into different types of energy. For example, a red colour filter will absorb all wavelengths, blue, green and yellow etc, but will transmit the red part of the spectrum, i.e. it will allow the red to pass through. So here we've got a blue filter. All of the other parts of the spectrum are absorbed, but the blue part of the light is allowed to go through. Here we've got a red filter, so you can see that all of the colours here are being absorbed apart from red, which is allowed to pass through. The colour of an opaque object is determined by which wavelengths of light are more strongly reflected. Wavelengths that are not reflected are absorbed. If all wavelengths are reflected equally, the object appears white. If all wavelengths are absorbed, the object appears black. Let's have a look at some scenarios now. So, scenario 1. If a car is red, the car takes in white light of all wavelengths and therefore colours. It absorbs other colours like green and yellow, but the car reflects red light. This red light then ends up in your eyes. So this is what you draw an eye like when you're doing scientific drawings. It's like this funny shape here. So what we can see is all of the colours of the rainbow come in and hit this red car here. Now this won't actually appear like a rainbow, it'll just be white light, but we're going to show white light as a rainbow just to show that white light is made up of all the different parts of the spectrum. So yeah, white light hits this red car. All of the colours of the rainbow are absorbed apart from red, which is reflected, and then the eye picks that up and we see that car as red. Let's have a look at scenario 2. If a carton of apple juice is green, the carton of apple juice takes in white light of all wavelengths and therefore all colours. It absorbs other colours like red and yellow, but the carton reflects green light. This green light then ends up in your eyes. So again, white light comes in, it's incident on this carton of apple juice, but then the carton of apple juice takes in, it absorbs all those colours and only reflects green, which then ends up in your eyes. Okay, scenario 3. This one's a little bit more complicated now. You are in a room with only yellow light, as there is a yellow colour filter placed over the light. White light enters the yellow colour filter, and all colours are absorbed except yellow, which is transmitted. So the yellow light goes through the yellow filter, but all other colours are absorbed. The yellow light then goes onto the pink genes. The pink genes absorb all light except pink, which it reflects. So no light is reflected into your eyes. You cannot see the pink genes or they appear black. And that's because only yellow light is incident on the genes, and the only colour that those pink genes will reflect is pink. And that means it'll absorb the yellow light and they will appear black. Scenario number 4. You are in a room with only pink light, as there is a pink colour filter placed over the light. White light enters the pink colour filter and all colours are absorbed except pink, which is transmitted or allowed through. The pink light then goes onto the pink genes, and the pink genes absorb all light except pink, which it reflects, so pink light is then reflected back into your eyes. And scenario number 5. Indiana Jones is wearing white clothes and a brown hat. White light is incident on Indiana. The different colours reflect different wavelengths. The brown colour filter between you and Indiana absorbs all wavelengths apart from brown, which it transmits. This means you will see Indiana as brown. Remember that white is all wavelengths. His white clothes still reflect brown as well as his hat. So that's all well and good for opaque objects. And when I say opaque, I mean objects which you can't see through. But what about transparent or translucent objects? Well, objects which transmit light are known as either transparent or translucent. An object is transparent if all light which is incident upon it can pass through it. Mediums such as glass, water and air are transparent. An object is translucent if some light which is incident upon it can pass through. Mediums such as cloudy glass and some plastics are translucent. So if you ever think about glass, so if you think about glass in a window of a bathroom, for example, the glass is made so it's hard to look through, and you would say that that glass is translucent. So let's answer some questions. What determines the colour of an object? The colour of an object depends on which colours are absorbed and which colours are reflected by that object. What happens if you view a yellow hat through a brown colour filter? The hat would appear black. The hat would reflect yellow light only, and the brown colour filter absorbs the yellow light and does not transmit it, which means the hat won't have any yellow light to reflect, and it would appear black. If you're following along in your Waves workbook, pause the video now and complete task number 11. Okay, next we're going to have a look at emission and absorption of infrared radiation. All objects, no matter what temperature, emit and absorb infrared radiation. Infrared radiation is waves which are made from the infrared part of the electromagnetic spectrum. Radiation in this sense just means waves which are emitted and absorbed. The hotter an object is, the more radiation it radiates in a given time. Something which is hotter than its environment will emit more radiation than it absorbs, transferring infrared radiation to its environment until they are in equilibrium, or the same temperature. If the environment is hotter than the object, then the object will absorb more radiation than it emits. This again will happen until they are in thermal equilibrium. A perfect black body is an object that absorbs all of the radiation incident upon it. A black body does not reflect or transmit any radiation. Since a good absorber is also a good emitter, a perfect black body would be the best possible emitter as well. Now, we know that all objects emit radiation, and infrared radiation especially is emitted from all objects. Other types of radiation are emitted as well. Visible light comes from most objects as well. The intensity of the radiation which is emitted from an object depends on the temperature of the object. The hotter an object, the more intense the radiation is which is emitted. Also, when an object is hotter, the wavelength of the radiation which is emitted increases. Now, we need to know about bodies which are at a constant temperature as well. A body which is at constant temperature is emitting radiation at the same rate as it is absorbing radiation. When a body is absorbing radiation faster than it is emitting, we notice that its temperature increases. So if an object is in thermal equilibrium, which just means the same temperature as its surroundings, it will be taking in as much radiation as what it is giving out. It will be absorbing as much infrared radiation as it is emitting infrared radiation. So, the body absorbs as much radiation as it emits. Its temperature will stay constant. On the other hand, we could have a body which is absorbing more radiation than what it is emitting, so the temperature will increase. If you're following along in your Waves workbook, pause the video now and complete task number 12. Okay, next we're going to have a look at the temperature of Earth. The temperature of Earth depends on many factors. The rates of absorption of radiation from the sun, the rates of emission of radiation out to space, and the rates of reflection of radiation back into space. What happens if we increase the amount of radiation which is being absorbed? Well, if we increase the amount of radiation which is being absorbed, we will get more heating. The temperature of the Earth will rise. Think, climate change. More greenhouse gases lead to heat being retained. What happens if we increase the amount of radiation being emitted? Well, if we increase the amount of radiation which is being emitted, we will get more cooling. The temperature will decrease. Think, during the night. More radiation leaves the Earth, so the temperature comes down. What happens if we increase the amount of reflected radiation? Well, if the amount of reflected radiation increases, less radiation will actually be absorbed by the Earth. The temperature would either remain constant or it would decrease. I want you to think about a bucket of water and how this is somewhat similar to the Earth. If you leave a bucket of water outside during a warm day, the water will increase in temperature. And this is because it is absorbing the radiation from the sun. The rate of absorption is greater than the rate of emission. During the night, when the sun has gone away, there will be a lower amount of radiation being absorbed, but radiation will still be being emitted. This means the temperature of the water will reduce. The Earth's atmosphere plays a large role in determining the temperature of Earth's surface. The Earth's atmosphere contains greenhouse gases which trap radiation. Examples of these gases include carbon dioxide and methane. Radiation which is emitted from the Earth can be trapped in by clouds and by the greenhouse gases. This means the more greenhouse gases that there are, and the more cloudy, the less radiation leaves the Earth's atmosphere, meaning higher temperatures. If you're following along in your revision workbook, pause the video now and complete task number 13. And once you've done that, you have finished the waves topic, so congratulations. Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backroadtutoring.com.